Okay, so in the last video, hopefully you've already learned that why the page table can be extremely slow. Basically, the performance problems of the paging mechanism. This is because a basic physical memory access require exactly a basic virtual memory reference. It gets effectively translated into two physical memory accesses. And the very first one is to just fetch the translation information from the in-memory per process page table. So this is the very first physical memory access. And followed by the second memory access, physical memory access. This is essentially the ultimate memory reference that targets the data of interest. Okay, so this basic memory access model, it's performance costly. It incurs too much performance overhead because in this mechanism, every data or instruction access gets translated into two physical memory accesses. Okay, so that motivates a need to really speed up this memory translation process, which is the very first physical memory translation targeting each and every data or instruction memory reference. Okay, so this can be solved by the use of a special purpose hardware, which is called translation look-aside buffer. It's a fast lookup hardware cache. It's essentially a hardware cache, TLB. And as you know, TLB is a part of the memory management unit, MMU, which is also part of the CPU processor. It's on die, okay? It's a special purpose hardware cache. It's a piece of hardware, so don't confuse it with some special purpose software. It's not a software. It's a hardware, okay? So the high level algorithm sketch is for each virtual memory reference. The hardware would first check whether there's a TLB hit. If fortunately there's a TLB hit, you just go ahead, fetch the corresponding TLB entry, which stores the content, which is the physical frame number, and then you just construct the physical address, and then directly by following this fast path, directly jump into the second physical memory access, which is the ultimate memory reference to fetch the interested data. So this is a fast path. The slow path, if unfortunately there's a TLB miss, then you end up with those, old slow step, which incurs, two different physical memory accesses. So in TLB basic algorithm, the first step, extract the virtual page number from the virtual address generated, produced by the CPU. Okay, so this is the very first step. No matter whether you have TLB, you always have to go through this first step. Okay, so the second step is something new introduced by TLB. So before really getting down to the memory page table pieces, you first go ahead and check whether the special purpose hardware cache, TLB, holds the desired translation information. This is the second step. If luckily it's a TLB hit, meaning the desired page table translation information has already been cached within the TLB, within a certain entry within the TLB, you just go ahead and extract the physical frame number from the TLB entry, and then construct the physical address by just basically concatenating the physical frame number together with the offset unchanged. Okay, so this is the second step, which is obviously the fast path. Okay, if otherwise, it's a TLB miss, meaning this page translation information hasn't been seen so far by the TLB. You just go ahead, get access to the page table, which is the very first, right? The memory access the page table to get the translation information, and then populate the TLB entry with the exact translation information that you've just seen. And this is a slow path, apparently. Okay. Okay, so let's revisit this old simple example, which is the array iterator. But with the support of translation local-site buffer, TLB. Again, if you take a look at this piece of code, it's extremely simple. It has just 4 lines, right? It's called array.c. And these 4 lines of C code is the core logic of this array iterator. It first declares a local variable which is called sum, and then enter the for loop. And it tries to iterate like a total number of 1,024 times. And within each and every iteration, it tries to sum the value under that specific array index and assign the value to the sum. Try to aggregate the values of the array all together. Okay, so this is the logic again. Let's revisit the memory access patterns. Again, this slide shows the virtual address pattern. Okay, again, this is under the support of TLB. And in this slide, we add extra piece of information, okay? So at the left-hand side, at the top, we have this process, which is called P1, page table, okay? Assume this process, virtual memory, consists of only 4 virtual pages from page 0, virtual page 0, all the way to virtual page 1. Okay, as you can see, a virtual page 0 gets mapped to physical frame number 5, and similarly, a virtual page number 3 gets mapped to physical frame number 1. Okay, so at the bottom of the left-hand side, it shows the CPUs, which is the part of the memory management unit. Okay, the TLB cache. So again, the capacity of this TLB cache is 4. It has 4 TLB entries, okay? And within each TLB entry, it has 3 fields. It has a valid field, meaning whether this TLB entry has been validated or not. And the second entry is the virtual address. And the third entry is the physical address. These 2 pieces of information is kind of like a page table information, Whereas in a page table, the index is the virtual page number, and the content, the page table entry's content is the major part of the page table entry is the physical address, physical frame number. Okay, it's kind of similar, but it's different in the sense that this is the virtual address. Okay, the virtual page number. On the right hand side of the slide, it shows the virtual access pattern. Exactly the same as the old example that we've seen in the last recording, okay? So the very first virtual access is targeting virtual page number 3. So as you can see, virtual page number 3 gets mapped to the physical frame number 1. But since the TLB starts off with all empty states, because of the given the TLB translation protocol, you will first consult with the TLB, which would be the miss, right? So let's take a look at the next slide. So it would be a TLB miss because the very first TLB entry is empty. And right now we're under the very first virtual memory access. So, but we know from the page table, because you need to fetch the page table into the memory, from the memory, and then correspondingly populate the very first empty TLB table, TLB cache entry as well. Okay, so that is where the very first physical memory gets hit. So you just access the corresponding page table entry. So assume this page table entry, because we're talking about virtual page number 3. Okay, so this virtual page number 3, it is located at this exact address. Okay, the 0x1000C in hex form. Okay, so this is where exactly this last page table entry within this for this process gets located within the physical memory, and then you populate the TLB entry. Okay, you first flip the value bit from 0 to 1, and then you enter the virtual page number, which is page number 3, and corresponding we know the content of the page table entry, which is 1. That means the mapped physical frame number is 1. Okay. Sorry, the mapped physical frame number is 7. Okay, so there's a typo over here. So this essentially should be 7. Okay, so then you go ahead, issue the second physical memory access, which is 7,000. Okay, and then starting from the second memory access, virtual memory access, which is the next array element. As you can see, there's an offset of 4 over here. Okay, there's always a stripe of 4 because each integer is of size 4 bytes. Okay, starting with the second virtual address access, there would be a TLB hit because this corresponding information has already been loaded within the TLB, which is the very first TLB entry that just gets updated, populated. Okay, so we end up with the very first physical memory access completely eliminated thanks to this TLB hardware support because we have a TLB hit, which is the fast path. And then with that, we just need one single physical memory access in order to perform one virtual memory access, which is the ultimate physical memory access to just fetch the array element, the 4-byte integer. Okay. Similarly, for the next 2 virtual memory accesses, there are 2 extra hits on the TLB entry because we're always targeting exactly the same virtual page, the same physical frame. So these 3 are essentially TLB hit. Okay, so let's say at some point of time in the near future, there's another virtual access which is targeting 2000, which is essentially virtual page number 2, right? Virtual page number 2 is over here. As you can see, it gets mapped to the physical frame number 4. If you search the TLB entry, this corresponding translation information has not been cached yet. So that means this very first virtual access to the virtual page number 2 will be a TLB miss. Okay, so correspondingly, you populate the translation information, which is the map between virtual page number 2 to physical frame number 4, which incurs 1 extra physical memory access because you need to fetch the corresponding page table entry and then populate the TLB cache, and then followed by the second physical memory access to get the corresponding, to get the data of interest. Okay, but it would only incur the very first compulsory miss, and all the rest, if targeting exactly the same virtual page or the physical frame, there would all be TLB hits. Okay, just shown over here. The next virtual address is 2004, and as you will see, there would be a TLB hit over here, right? Because the data has already been cached within TLB. So TLB hit, and then you just completely eliminate the very first physical memory access trying to getting access to the page table, and then followed by just a single physical memory access, which is targeting the data of interest. Okay. So in this example, you'll be asked, how many TLB lookups for this array iterator kind of pattern, assuming 4 KB pages. So in this case, you basically iterate through this array of 1024 elements, and each element is a 4-byte integer. So that means this array itself, from A0 all the way to a 1023. Okay, so this array itself is 4 KB worth of memory. Okay, 4 KB. So the question is, since array has 1024 elements and each item is 4 bytes, the question is how many TLB hits we could have, how many TLB miss we could have, right? So the total number of TLB misses could be either 1 or 2. Why is that? It's because if the starting address of this array is well aligned with the starting address of, basically aligned with the memory page, then there would be just one single TLB miss, okay? If the starting address of this array is not aligned, that means this memory block holding this array spans like 2 adjacent memory pages. So for the whatever memory access is hitting on the first memory page, there would be a TLB miss. And for whatever memory access is distributed at the within the second adjacent memory page, there would be another compulsory TLB miss. So we end up having a total number of 2 TLB misses if, and only if, the array is not aligned with the boundary of a 4 KB memory page, okay? So the TLB miss rate, we end up having 1, assuming the best case scenario, assume we have only 1 TLB miss. So it will be 1 divided by 1024 gives you 0.09%, which is extremely small. So that effectively means the TLB hit rate is almost 1%. It's almost 100%, 99.91%. Okay. So next, TLB content. What are exactly held within each TLB entry? So first of all, some entries are preserved and wired down for permanently valid translation. For example, a specific system software that is always running. So you preserve that TLB part just for facilitating the memory translation for that particular software. And also, TLB cache is a fully associative cache. So what does that mean? It means each and every memory page could be anywhere within the TLB. So that's why it's a fully associative. There's not a affiliation mapping or any kind. It's fully associated. Any given translation could be anywhere in the TLB. And also, one of its major performance benefits also comes from this fact that the hardware searches is effectively happening in parallel. So assume a TLB has a total number of 10 entries. And in order to perform a single TLB search, all these 10 entries will be searched exactly the same time in parallel to find a match. Okay, so regarding the content within the TLB entry, it consists of the following information. Okay, so the virtual page number mapped to the physical frame number and some other bookkeeping information. Okay. Okay, so the next slide, it shows from the hardware perspective how to perform a TLB page translation under the support of a TLB. So first of all, the CPU generates the virtual or logical address, which consists of 2 parts, the high bits, P, and the low bits, D. And then before getting down to, consult with the page table, you don't go with the page table first. Instead, you always search the TLB first, okay, in parallel. If luckily there's a TLB hit, you will just fetch the corresponding physical frame number, okay, assume the 4th TLB entry is a hit, and you just fetch F and concatenate with the unchanged, the offset part, which is D, to construct the physical address. And then you use the physical address to look into the physical memory, okay? This is a TLB hit. What if, unfortunately, we have a TLB miss? Well, we just end up with exactly the same step that we've seen in our last recording, without existence of a TLB hardware cache, okay? First of all, you need the very first memory access to get into to get access into the page table. And then you fetch the same piece of information, which is F. Construct the physical address by concatenating F with D. And then the rest of the steps are exactly the same, no matter whether we have TLB or not. That is why we always have one or at least one physical memory access for each virtual memory access. Okay. So even though with TLB, there are certain issues. The very first issue is because the page table is a per process data structure. And if ever the operating system wants to perform a context switch, to switch the control from, let's say, process 1 to process 2, you have to flush all the content within the TLB because the current content within TLB is all reflecting the translation information on behalf of process number 1. In order to switch off process number 1 and bring in process number 2, you have to flush all the content within the TLB, which could be dramatically costly, significantly costly. Okay, so this is some issue. So in order for operating system to effectively distinguish which entry within TLB is for which process, the baseline case is we cannot do so. Okay, in this case, we have two different processes, P1 and P2. Both of these two processes, they have the same VPN. As you can see, both the same VPN 10 gets mapped to a certain physical frame number, PFN. And both of these are valid entries. How to distinguish between these two different processes is a problem. There's no way if just given the current form of TLB as is, right? So just as I've already mentioned, one simple solution is whenever you perform a context switch, you just perform a full flush of the TLB content to evict all the content. And we start off with an empty TLB, okay, by just sets all the valid bits of the TLB entries to 0. But the problem of this approach is the performance overhead is too high because all the very first set of memory accesses for the new process, they are all TLB misses. So that introduces performance overhead for that particular newly brought in process. So one optimization that we can do is to introduce this so-called ACID field, okay? So this ACID is the abbreviation of address space identifier, okay? With a short of ACID. So we preserve this field within the TLB entry and use this field to distinguish between different processes. So this is kind of like a process identifier, PID, okay? So in this example, again, we have two entries with exactly the same virtual page number. How to differentiate, how to distinguish between these two is by looking into this ACID field. As you can see, the very first value 10 is associated with an address space identifier of 1. That means this might be associated with process number 1. And the second one has an ACID field of 2, meaning it's associated with a different process. Okay, we use ACID field to distinguish between different processes so that whenever performing context switch by the operating system don't have to flush all the content by flipping all the valid bits from 1 to 0. Okay, so within TLB, it could also facilitate memory share, page sharing or memory sharing. Okay, in this example, these two different virtual page numbers, 10 and 50, as you can see, they both map to exactly the same physical frame number, which is 101. Okay, so this means these two different, so as you can see, the ACID field also different, 1 and 2. It means these two different processes, they are sharing the same physical frame, the same memory. Okay, so this is how you support memory sharing. How do you reflect memory sharing within TLB? Okay, you can also share code, right?